So the contact point, so the reason we or I and Gal and I care about free probability is because of its relevance to spectral graph theory, in particular to expander graphs. So the main paper or sequence of papers that we cared about when we started to delve into this research field is a sequence of papers by Marcus Spielmann and Srivastava from around 10 years ago, in which they constructed or proved the existence of certain extremal graphs. So let me start talking about that. So in this part, I'm just going to give you a very brief introduction of spectral graph theory. In expanders, there is a whole course on spectral graph theory, which I gave, and it's also available on YouTube, but I think it's in Hebrew. So this is going to be just in a nutshell. So that's the idea in spectral graph theory. And again, I'm mostly saying that because I want to give the context of free probability within theoretical computer science. So, when you do graph theory, what you do is you have this graph G. This is the Peterson graph, by the way, and you work with it. You do your thing. You look at the vertices and the edges and the bridges and maybe clusters and so forth. And it's actually really hard to do it. The kind of better thing to do, maybe in some settings, I don't know, is to linear algebraize the graph. Or more precisely, the first thing you should probably do is to look at the adjacency matrix of the graph. Right? This is the matrix that's indexed, rows and columns are indexed by the vertices of the graph. And you have 1 or 0, depending on whether there is an edge or not between the two vertices. And actually, you can put any number here to either symbol to either encode a weight or maybe a double edge that appearing and so forth. So that's actually we're actually kind of used to doing that because that's the way we store graphs in memory, or at least if they are dense. But taking it a step further, this is if G is an undirected graph, and throughout the course, we're all going to talk about undirected graphs, and generally in computer science, you stumble across those more often than not. So if G is an undirected graph, then AG is a symmetric matrix, right? And if you remember from linear algebra, symmetric matrix can be decomposed like that. That's the spectral decomposition theorem. So a symmetric matrix has, say, of size n, n by n, it has n real eigenvalues, not complex, real eigenvalues. That's denoted by lambda I. And not only that, it also has an orthonormal basis of eigenvectors. Right? So psi I is an eigenvector corresponding to lambda I, and this thing is really a projection matrix, rank 1 matrix to psi I. And so you can write AG like that as a sum of rank 1 matrices of projection matrices, really scaled correspondingly to the eigenvalue. So the picture you should have in mind is this one. So you have a basis which encodes G better than just the standard basis, right? That basis encodes the entire edge structure, graph structure that you have. And the operator AG, so it's a matrix, but I think of it as operating on vectors. So the operator AG is very simple, in any direction which is an eigenvector. It's merely you merely just shrink or stretch or maybe reflect if lambda is negative and so forth. The spectrum of the graph is going to be just the set or multiset of eigen values, and we're going to denote the larger one by lambda 1 and the smallest one by lambda n or lambda v. V is the size of the graph. Okay. So the point is that the spectrum alone, just the eigenvalues, not the eigenvectors, can teach us a lot about combinatorial properties of the graph. So for example, the largest eigenvalue, lambda 1, happens to encode information about the degrees of the graph. For the purpose of this lecture, let me just mention that G is a D-regular graph, namely every vertex has D neighbors, precisely when lambda 1 equals to D. Okay. So that's usually, that's not an information that you can't see by yourself. You look at the graph, you see that it's D-regular. So lambda 1 is usually referred to in this context as the kind of trivial eigenvalue. It gives you no non-trivial information about the graph. The interesting thing is the other eigenvalues, or more precisely, their bounds. So note that lambda 2 is the largest of the rest of the eigenvalues, the way we order them, and lambda n is the smallest one. So all the eigenvalues are kind of sits in between lambda n, lambda v, and lambda 2. And it turns out that that interval, or more precisely, the distance from zero of that interval, so the maximum between lambda 2, which is always positive essentially, and lambda n, which may be negative, hence the absolute value, this number, the maximum between lambda 2 and lambda n, is a very important property or parameter of the graph, and it's called the spectral expansion of G. Okay, just as a side note, I would say that for D-regular graphs, lambda 1 is D, as we said, and you can show that lambda n in absolute value cannot go beyond D. So the game plays between minus D and D, and in fact, we know that lambda 1 is D, so we really care about the other, where the other eigenvalues live. Okay. Also, a nice remark is that lambda v equals minus D exactly when the graph is bipartite and irregular. Okay. So I said that lambda g is a very important parameter of the graph, and the point is that if it is small, then good things happen. For example, if lambda g is small, and we will talk about how small is small, then you'll have the graph will have properties that are shared by a random graph with high probability. And so a lot of the properties you kind of enjoy by taking a random graph, you'll have in your like deterministic graph, as long as that graph has a small lambda g. So in particular, you will have a kind of expander Chernoff bound, and you'll have a random walks will mix quickly and so forth. But let me just keep it at that and just say that we really want graphs, the irregular graphs where lambda g is small. And for applications, usually the degree is something you pay for. Whatever you do, if you work with codes, you might pay it for in distance or rate or query complexity and so forth. But regardless of what, you should think of the degree as something you want to. It's a parameter that you care about. It's like a resource. You don't want it to be too large. So the questions of how small can lambda be is with respect to the degree d, and the answer to how small can lambda be is given at least one-sidedly by the Alon-Bopana bound. So the Alon-Bopana bound tells us that the magic number is 2 times square root of d minus 1. Okay, so that number. So what do I mean? So there are many ways of formalizing that, more accurate and accurate ways, but let me use the simplest formulation, which tells you that if you're asking for a graph which is deregular and is better, lambda g is smaller than 2 to the square root of minus t by an additive epsilon, then for any epsilon that you fixed ahead of time, then you can only find constantly many graphs that have this property. Right? So you can shave this epsilon, any epsilon that you want, you can shave it too often. Definitely not asymptotically. Okay? Now, as the number of vertices of the graph goes to infinity. Okay. And it turns out that this bound, this magic number is tight. Namely, there are d-regular graphs which achieve the bound, namely lambda g is at most the magic number. And these are dubbed Ramanujan graphs for historical purposes. Okay, so Ramanujan graphs are kind of the extreme spectral expanders. They have the best spectral expansion possible asymptotically. So let's look at two examples. And again, just this whole discussion is just to give the context of the free probability to theoretical computer science, but I kind of assuming some of you know these things. Okay, so for example, this is the length 6 cycle graph, C6, and it has a degree 2, so you'll see it has an eigenvalue of 2, and it's bipartite, so it also has an eigenvalue of -2. And it turns out that the other 4 eigenvalues, there are 6 vertices, 6 eigenvalues. The other 4 eigenvalues are 1 and -1 with multiplicity 2 each. Also note, and these are the yellow lines here, that 2 square root of d minus 1 in this case is, just square root of, 2 square root of d minus 1 is just 2. So the Alon-Bopana bound is really kind of useless in this case because 2 square root of d minus 1 is just d, for d equals 2. So all the eigenvalues sit where the Alon-Bopana bound tells you that they shouldn't asymptotically. But of course, for degree 2, the Alon-Bopana bound is anyhow useless. What kind of graph do you expect to have over degree 2? It's just a union of cycles anyhow. So if it's connected, it's only this one. A more interesting example is the Peterson graph. This is a degree 3 expander or graph. So the Alon-Bopana bound tells you that all the eigenvalues, asymptotically at least, should sit outside 2 square root of 3 minus 1, which is square root of 8. And if you kind of examine the graph, you will see that it has an eigenvalue of 3 because the degree is 3. That's this one. And it's a very symmetric graph. So it is reflected by the spectrum. And you see that all the eigenvalues, all the other 9 eigenvalues are either 1 or -2 with multiplicities 5 and 4, respectively. Again, this is a bad example in terms of Alon-Bopana because all the eigenvalues, except for the trivial one, sit where they shouldn't, between the yellow branches here. It's a small graph. So another thing that I should tell you about, and you may wonder about Ramanujan graphs is, whether they are special or not. Namely, if I sample a d-regular graph according to some natural distribution, say, for example, a union of d-perfect matchings, that's a way of sampling a d-regular graph, not all regular graphs, not all d-regular graphs, but sufficiently many in a sense, then would I get a Ramanujan graph or not? So is Ramanujan a structured property or is it a typical property? And it turns out the answer is, according to experiments, the answer is that for that distribution that I told you about, there is a number which I don't remember, like a fixed number. I don't know, 17%. It's not the right number probably. Such that sampling according to that distribution with that percentage will give you a Ramanujan graph. So Ramanujans are not extremely special, but they're not highly typical also. But what do we know how to prove? That's just experiments. What we know how to prove is that, and that's a result of Friedman, it's a difficult result, answering a question by Noga Alon, is that with high probability, a d-regular graph under the distribution that I told you about, or related distributions also, is going to be close to Ramanujan. And by close, I mean that the bound on the lambdas is 2 square root of d minus 1 plus a little of 1, which vanishes as the size of the graph grows. Okay? Now, as theoretical computer scientists, we want explicit constructions of graphs. We don't just want their existence. It's a good starting point, but we don't just want to know that a graph exists, much like we don't want to know that there is an algorithm. We want the algorithm. So algorithms in particular that use expanders need the expanders. And expander graphs actually have a very interesting, weird history in terms of constructions. So essentially, already from the get-going, in two papers by Lubotsky, Philip, and Sarnak, and one by Margolis, using extremely deep number and group theoretic results, Ramanujan graphs were constructed. That never happens. Usually you have a definition of something like expander in this case, but extractors or pseudo-anom generators or whatever you do. And maybe in that introductory paper or in follow-up papers, you have some constructions, but they are not optimal initially, and usually it takes a lot of time, decades, to get constructions which are also usually not optimal. Okay, they're just close to optimal. And here, already from the get-going, these two papers gave an explicit construction, very explicit. I'm not going to go into this different definition of explicit, but think of the intuitive notion of explicitness. They give a very explicit construction of expander graphs, which are Ramanujan. So already from the get-going, the story ended. But not really, because when you work with expanders, sometimes you need extra features. You want to kind of play with them, to add something to them, or to make something not with the expander itself, but with the techniques that were used to construct it, and so forth. And as I said, the underlying techniques of these constructions is it's complicated. It's not something that it's kind of rigid, especially if you're not a researcher in those fields. So it's hard to play with. So people started to ask, can you construct expanders by elementary means, something that you can play with and do what you want with it. And the code name for simple elementary is combinatorics in this setting, right? So technically, you can't give a completely combinatorial construction and analysis of a spectral expander, because by definition, spectral expansion is linear algebraic, the second eigenvalue and so forth. So when I say a combinatorial construction, I mean a combinatorial plus elementary linear algebra, and everything in linear algebra is anyhow quite elementary. So the golden boy of this branch is the zigzag product. So this was introduced by three legends of theoretical computer science, Reingold, Vadan, and Wigderson, some 20-something years ago. And that's a way of, that's an operation on graphs. It's a way of taking a large graph and a small graph and combining them in such a way that you preserve the properties that you like in each of the graphs. I'm not going to get into it right now. And there are other ideas. Closer to that, there is the de-randomized squaring by Rosenman and Vadan, and lifting by Bilu and Linear, and so forth. I think I have a course on that, but it's in Hebrew on YouTube. I didn't cover lifting, but I covered the zigzag product. Anyhow, so these are the combinatorial constructions, and they were very useful. So for example, the zigzag product, immediately after its introduction, it was used, the operation, not the expanders, was introduced by Reingold in his famous SL equals L theorem. Okay. So what I'm trying to say is that the idea of getting a simpler or more elementary construction was useful already from the get-going as well. However, these constructions weren't Ramanujan. There are different parameters. So the zigzag, you want something like 2 square root of d minus 1. So zigzag is quite off. It's like something like due to the 3/4, or maybe you can do slightly better. Lifting is better. It's like d log cube or something of d. But it's less explicit and so forth. Never mind the differences. The important thing is the technique. So the technique here was heavy group theory and number theory. Here it was very light combinatorial, very smart, but light in terms of the mathematics that's been used. Combinatorial and linear algebraic arguments. And we played with those for a while. And then 10 years ago, which in my head is not a lot, 10 years ago, there was a third branch kind of opened. And this is the paper that I was alluded to before by Marcus Spinell and Srivastava. It's actually a sequence of papers. And they used analytic machinery to prove the existence and then afterwards also construct expanders. The construction was a different paper by Michael Cohen. So what do I mean by analytic machinery? Well, we will see, so don't worry about that. But the benchmark is that you have integrals and you do like things in continuous domains and you do some measure theory and so forth. Okay, I don't know. I'm not sure that's the right definition of analytic, but that's my way of separating it from the combinatorial and number theoretic results or techniques. So the main point for us is the new technique, but the selling point of the paper, I mean, it's really hard to sell something when from the beginning you got optimal construction, right? But the main selling point was that the original construction had this annoying technicality. They only worked when D was a prime, maybe prime plus one or prime power plus one, because they needed some structure. The construction of MSS works for any degree and also for every graph size. Essentially, if it's bipartite, it's going to be even numbers, but anyhow. But the downside is that they were only able to bound one of the eigenvalues, either lambda 2 or lambda n, whichever you want, but not both simultaneously. That's sometimes called a one-sided expander. It's useful for some applications, but not enough for others. Because of the symmetry of the eigenvalues, but it actually required a bit more work. They also constructed what's called a bipartite Ramanujan graph, but I'm not going to go into that. Okay, so what the takeoff from this part is that the analytic machinery that they introduced, that MSS introduced, is something that you may want to understand because it could serve you, solving your favorite problems. And it actually was very useful for us to solve some of the problems that we considered recently.